So for notes 6.2, we're going to talk about these two things. These are our two objectives. So determine if a statistic is an unbiased estimator of a population parameter, and then describe the relationship between sample size from the sample, how big the sample is, and the variability or the spread of the statistic. Okay. So first thing we're going to talk about is biased versus unbiased. Okay. So let's say I have a population. Okay. The population is distributed in some way. Okay, so we have some sort of distribution of a population. Now, if I take some samples from here, I take a sample of 5 or 10 here, I take a couple of different samples, and I get this, right? Okay, now, so I take a sample of 5 and find its mean. I can find a sample of 5, find its mean, find a sample of 5, find its mean, find a sample of 5, find its mean. Okay, so I get that idea. Now, it is unbiased. It is unbiased, here's the definition for it, if the mean of its sampling distribution, okay, remember this is the sampling distribution right here, right? Okay, so we have a population, we take a sample, find the mean. Take another sample, find the mean. Take another sample, find the mean, right? This is our sampling distribution. Now, it is an unbiased estimator if the mean of the sampling distribution, the center, or the mean, is equal to the value of the parameter we're trying to find. So if I'm trying to find the mean of this sample, and if the mean of our population is equal to the mean of my samples collected, then we would say they are unbiased if those are equal to each other. Okay? So, for example, if we look at these two up here, which one is biased and which one's unbiased? Okay? So we want to, our parameter we're trying to find, our population is this number right here, the red. So does the center of this distribution look like the center of our population? Okay, no, I would say this one is biased. Okay? Now, does the center of my sampling distribution, okay, the center here would be about there, equal the population, the red line, mean? Yeah, okay. So those two are equal to each other, so this one would be unbiased. Okay, so I'm going to show you a video that kind of looks at that a little bit as well. Okay. The other thing we're going to talk about is sampling variability. Okay. Variability is standard deviation, or, that sort of thing, how spread out the data is. Okay. So what does sample size have on that? Okay. So here are two different examples. This is a sample size, like from our population, right? If I have a population here and I take a sample of size 10, so I take 10 data out of here and find a mean. I take another sample of 10, find their mean. Take another sample of 10, find the mean, right? And I get a distribution. Versus if I take a sample of 50. So if I take a sample of 50 from the population here, I get the same mean. Take another sample of 50, find the mean, right? So what do you notice about the variability? Okay, the variability is how spread out it is, right? So notice, the smaller I have in a sample, the more spread out it is. The more I have in the sample, the tighter it is together around the true center that I'm trying to find. Okay? So the other thing, number 2, is the sampling distribution of any statistic will have less variability, be less spread out if it's a large sample size. And if we think about that, that makes sense, doesn't it? Like the more that I take in a sample, the more accurate it's going to be to that true number I'm trying to find. If I'm trying to find the mean of, say there's 1,000 numbers in here, if I take 2 numbers, it might be those 2 numbers there, right? It's going to be pretty soft. But if I take 100 numbers and find the mean, that's going to be closer to the center here. It's going to be a lot more accurate the more numbers that I take in the sample. Okay? I'm going to break here and show you a little video. Okay, let's go back to this example here. So for quality control, workers at a battery factory randomly select samples of batteries to estimate the mean lifetime. So we're trying to find, this is our parameter, the mean lifetime. So how long does a battery last on the mean of it? Here's a simulated sampling distribution of a bunch of X bars. The sample mean in hours of 1,000 random samples so we're taking a sample of 100. Okay, so they make all these different batteries, right? So our population has a wide range of batteries. Okay, so there's our population. We're going to take a sample of 100. So we're going to take 100 batteries, and we're going to find their mean. Okay, we're going to do this 1,000 times. We're going to take another sample of 100 batteries, find its mean. We're going to take a sample of another 100 batteries, find its mean. So this is our population. Okay, so what we have here is it's a normal population. We'll change it to skew a little later. So let's say we take a sample of 5. So here we're going to find the mean of a sample of 5 taken from this population. So we'll take 1 sample, 2, 3, 4, 5 samples, find the mean of those, and it comes up to be this number. do it again. 1, 2, 3, 4, 5 samples randomly taken from the population. 5 samples gives us another number. Now, if we do that 100,000 times, this is our sampling distribution. Okay, it is unbiased because the mean of this, right? Mean of this is 16, and the mean of our sampling distribution is also 16. We're very, very close. If I do another 100,000, it'll be 16. Okay, so unbiased because they have the same centers, right? If our mean is our parameter we're talking about. Okay, now let's say I do one is 5 and the other one is at 20. Okay, so if we take a sample of 5 here, there's the mean of those. If we take a sample of 20 from our population, find the mean of all of those, that'll be shown down here. And if I do that 100,000 times, okay, notice both of them still are unbiased, right? Center here at 16, mean is 16. Mean here is at just around 16, and this is 16 as well. So they're unbiased estimators. Okay. The other thing we're looking at is how spread out it is. Notice more in a sample at 20 versus 5, right? More in the sample, notice it's less spread out, right? The more that we have in a sample, the more accurate it is, the closer it's going to become to that actual mean, right? So we have it less spread out. You can see the standard deviation of 2.23 versus 1.12. Okay. Let's say we change it to be a skewed distribution. Okay, so we can do it again. Here's 5 samples from the population. There's the mean. Here's 20 samples from the population. And down here will be the mean. Okay, and if I did that 100,000 times, okay, there's our distribution. So see the mean up here is at 8.08. The mean down here right around there. And the mean down here right around there, right? So they're unbiased estimators, right? If we're trying to find the mean of this data, the mean of these X bars are all, right around the same mean, so unbiased. And secondly, the more I have, right, 20, the smaller the standard deviation, the smaller the spread. Okay, the less I have, the more spread out it is. Okay, let's go back to this example here. So for quality control, workers at a battery factory randomly select samples of batteries to estimate the mean lifetime. So we're trying to find, this is our parameter, the mean lifetime. So how long does a battery last on the mean of it? Here's a simulated sampling distribution of a bunch of X bars. The sample mean in hours of 1,000 random samples of, and so we're taking a sample of 100. Okay, so they make all these different batteries, right? So our population has a wide range of batteries. Okay, so there's our population. We're going to take a sample of 100. So we're going to take 100 batteries, and we're going to find their mean. Okay, we're going to do this 1,000 times. We're going to take another sample of 100 batteries, find its mean. We're going to take a sample of another 100 batteries, find its mean. We're going to do that 1,000 times, and we get a certain distribution here. Okay, what would happen to the sampling distribution if the sample were 50 instead of 100? Okay, so if I take less people, right, less batteries, okay, it would be more spread out. Okay, more spread. So n equals 50 versus if I had n equals 100. Okay, 50 more spread out, 100 not as spread. Okay, and what would be the practical consequence of this? It would be less accurate. Okay, so if I take a sample of only 50 batteries, it's going to be more spread out, which won't necessarily find that true mean, right? I could get a number down here, I could get a number up there, I could get here, I could get here, but if it's n equals 100, it's more likely to be right around the true sample mean that I'm trying to find. Okay, so what we're trying to look for is this. Like when we're trying to find a certain number about a population, we're trying to hit the bullseye, right in the middle. We're trying to hit that bullseye right in the middle. Now this one, it doesn't hit the bullseye, so it is biased. Okay, it's biased. It's not hitting the true number we're trying to find. It consistently finds another number that's not the number we're trying to find, so that is biased. But it has a low variability. It's not very spread out. They're all bunched together a certain area here, so it has low variability. That's not what we want, though, because it's not here. Okay, this one, if you find the mean of all these numbers, it kind of hits the bullseye, right? So it's not biased. We can call that unbiased, because the center of all these different things here, it hits the center of our bullseye, what we're trying to find. Okay, but the bad part about this is that it's pretty spread out. It has high variability, which means we maybe had a smaller sample each time we took a sample, right? Okay, this one here, the center of our sample's nowhere close to the bullseye which we want. Also, it's pretty spread out, so it has high variability, definitely not what we want. This one, this is the ideal thing, this is what we want. We want the center of all of our samples to be the center of our bullseye, and we also want them to be bunched together, so low variability. So if we take higher numbers in our sample, we get closer to that true number that we're trying to find.